Good morning, everyone. Once again, I can suggest that we can start with our today summer school in the middle of the winter. But okay, this is the this is the form of our today activity. Again, within our project, increased excellence in advanced additive manufacturing. But with today's um, okay. I will just reclaim my host for a moment so that I can show you just today's agenda. Can you see my screen? Yeah, okay. So today's summer school is titled Medical Modeling for Additive Manufacturing, and it will be a little bit more specific compared to the previous workshop 3 weeks ago when we were speaking about general application of additive manufacturing in medical sector. And you all received agenda a few days ago, but because of some of the issues and obligations of our authors, we changed a few we changed just a schedule of presenters. So this is today's final agenda. I hope that you will find something interesting because this is more specific application of additive manufacturing in medical field, not so on general level like last time. So this is also reasonable that it's obvious that we have today a little bit less participants, attendees, but nevertheless, I was present at one conference this week, and this is international conference, maybe with a higher, I should say, higher reach of the potential attendees, and they have maybe 40 to 50 participants. So I should say that today's 20 participants in this summer school so far. Maybe we will have it during the day even more. It's quite okay. So I will now stop sharing my screen. Just a second. Stop share, okay. And I will invite Mika Salmi as a host to present the first topic of today's lectures. And before you started, I would like to thank all of the presenters to participate in our activity, and as well as all participants. So please, Mika, you're first. So please break the ice of today summer school with the title Challenges in Designing Medical and Industrial Components. Mika,
okay.
The floor is yours. Thank you.
Thank you, Damir, and thank you for the invitation to present in this session. Let me share my screen. If someone can say that you are seeing something. Okay, so today's topic is the design for medical, but why I have an industrial here also. So basically, there are similarities related to also in the industrial components in the design aspects. So that's why the topic is also highlighting some industrial challenges, because that can be copied, or we can learn from the medical side also from those. So my name is Mika Salmi. I come from Aalto University, Finland. And shortly about the content of this presentation. So first, let's look what we do in Aalto. then why the design is important, a little bit about the personalization and data capturing methods. Then we can think about cases where we need to design example spare parts, and then there is a limited data available. Then shortly about methods for topology optimized sand castings and what's related to that design. Shortly about the open source, then process specific parameters and process simulation, and then future challenges and some conclusions. So I come from Aalto University, Finland. Let's see, can I get rid of this R? Not easily. Okay, let's don't this to this purpose. So basically, we have done research in additive manufacturing since 1992. Currently, there is about 15 research with more than 100 years of AM experience. We have many different processes in a house with more than 30 different printers, and the group is led by Professor Jouni Partanen, who has worked 12 years in the 3D systems in the early days and has more than 50 patents in this area. And then what we do, basically we looked at, okay, there is some application. Example, now we are discussing about the medical applications, or is it the end use parts or some key performance components. But for the application, you need also material, and you need to check the quality. Maybe you want to use some new materials even. And then to process, you need the technology. You need to think about the post-processing. Maybe you want to combine and develop some known process. And then before you can make anything, you also need to design, which is today's topic. An example, the design can be used for the optimization. Then if you look about the design, so why the design is important? From the AM perspective, it always requires a 3D model. So we need to design the 3D model. And then if you think about the potential, if we want to really optimize and make the best parts that we can, the design is the key for this. So if we want to make more lightweight, we need to think about the design, not only the AM manufacturing. And then if you think about the personal products, its design then is a different one. And then we can simulate different AM processes, especially the metal powder bed fusion. But it requires design as an input. And also then we can use those simulation results to improve the design. So we can iterate there. Is it the AM process simulation, or is it like the product simulation? So we can use those to improve our design. And then shortly about personalization and data capturing methods. So basically in the medical field, mostly those are like the computed tomography, magnetic resonance imaging, 3D ultrasound, and nuclear imaging. And with those you can see inside the body. And usually they provide the layer images in DICOM format. And then the segmentation is needed to calculate 3D geometry. But then we can also use different 3D scanning and measuring methods, photogrammetry, light space scanning, structured light, contact scanning, time of flight. And with these we can see external surfaces. And usually those provide the surface in triangulated format, but the 3D printing requires a closed surface. So we need to, if there is a gaps or anything, we need to fix those before we can use the data for the 3D printing. And this is a case study for a medical implants, and where are those error sources are. If you look about the medical imaging, that has I would say least error. Of course, the 3D modeling error is close to 0, so that's the smallest one. But then when we are segmenting that image, so there is a thresholding error, and then that actually can be quite significant. And then we need to think about if we have a two boundary surface, so we need to put something between. Example, so there would be this thresholding error twice. So that's need to be taken account because it's in the two surfaces there. And of course, then the additive manufacturing process can can cause errors. Then if you jump to a little bit about the spare parts, and there the case might be that there is not the 3D model available, there is not too much data about it. So example, there can be a 2D drawing of the part, so that can be easily like a remodeled. We can try to scan the data and have like a vector files, or we just read the drawing and 3D model it based on the drawing, and we can get the geometry out of that. Or we have the digital drawing and then we can import that to 3D modeling software. One option also is that we have some kind of physical parts. So that would be close to that. We have like an example, we need to make a personalized medical implant. So we have the patient there as a physical part. There we can use traditional measurement methods. Yes, but not with the bones example. There we need to go this medical imaging where we can see inside the body. But for our physical spare parts, 3D scanning, different kind of methods can go there and we can get the model out of there. Or then if we have the 3D model, yes, but it might need some tolerances and those. Or then we have different combined inputs, which might help. Of course, in the optimal situation, we would have all of those, and then it would be easy to replicate the part. And this is a case study about topology optimized sand casting using additive manufacturing. And why I have taken this example? This example includes a lot of design aspects related to this, and a lot of simulation and iteration loops. So basically, this is like a suspension linkage for a Formula Student car, and then there is this basic design. And then, of course, we can topology optimize that to have it more lightweight. And then we want to keep the manufacturing method same, but now we don't think about how we can cast that part. We think about how it could be the most lightweight version. So then we can optimize it, have the raw version example of that. And of course, we could maybe manufacture the raw version, or we made to redraw the component, have it a little bit smoother and so. But because we are discussing about casting and these kind of components for casting are actually quite complex compared to this basic design. So maybe we want to do some casting simulation. And of course, we need to design the mold so that we can cast the part actually. So as I said, this basic part, this is from the aluminum alloy, and this is easy to make with sand molding patterns. And then if we simulate with the same loads as this original one, then we can get this raw data out. And the optimization is based on like, okay, we have some kind of design phase. So like where the part could fit there. And then we have the load and boundary conditions. So we know how it's attached, what are the loads and so on. And then we know that, okay, it's a symmetric. So we can use shape control that help the calculations. And with that, we can get the optimized part. And then in this study, we manufactured all of those. So we manufactured this original as a reference. And then we have this optimized one with the raw data and use that for the casting simulations. And then we have this complete redesign shape. And this is an example of like a casting simulation for this raw data. So we need to check that the material will flow there, and there would be like example air would trap there, and we need to design air vents and all the casting process, how it works. But of course, then we need to simulate the cooling so that there wouldn't be too much stresses in different places. So how the part would cool there. And then when we are happy for those, or maybe we need to modify the design, we can go to the mold design. So this is the mold design for all of those design geometries. So we used and 3D sand printing to make the mold. And then we can make those parts. And then if you think about from the design perspective, one interesting aspect is this open source 3D models. So there is a different data already available. There is already like a ready models available. Maybe you need to a little bit tune them, but basically there are like different open source solutions. But then if in the open source, usually there is a question related to IPR. So shortly, if you look about like the real longer text about this, that's actually quite good source there. So basically there is like a copyright, and basically what it protects, it's an original creative object. And basically like a CAD file from the scratch could potential go here, but not the 3D scan of existing object. But it doesn't protect the materials used for the production. And then there is a design right. So basically the external shape and features, appearance of the materials, but it doesn't protect any raw materials or internal parts which are not visible in the normal use. And then there is a patent right. So basically innovation and technology contained in the object. And basically like a CAD file that contains a plan for a patented item, and that could go there, and certainly if it's cited in the patent claims. But then that doesn't protect the aesthetic layout. And one example about the power of this open source. And so basically example in this COVID case, we have seen in the medical side, so different medical products, nasal swab for taking the samples, different face masks, holder for the face shield, venturi valves, venturi splitters, different kind of solutions were made and shared in an open source way. And actually that boosts quite a lot, and it allows to create a different kind of solutions in the open source way, or you could use the existing ones. And I believe this is a good example how this open source design can affect. Then of course we need to think about like, okay, if we are like example making implants with the powder bed fusion using laser from the example titanium alloys, maybe we want to make some kind of process simulation so that the geometry would be as accurate as we want. So basically there would be always different distortions and stresses, but we can simulate them. But usually that works that you have a software which can simulate those, but you need to calibrate it. And that's calibrated with one material, one machine, and one parameter set. And of course, this design geometry, orientation, design of supports, those affect. And also like how to remove the parts, heat treatments, and so on. And that leads that maybe based on simulation, you want to redesign something. Maybe you can predict that something would break during the printing, or it ain't going to be successful. So maybe you want to redesign it. And also there is one possibility that you can like predeform the geometry in the opposite direction. So you can try to simulate what are the distortions in there, and then with the preforming in the opposite direction, you can compensate those. So after the printing, it should be as you are planned. And the more complex, the more iteration there might be. But this is actually one aspect to think about, because now you have maybe the original geometry and original design, but then you have also the simulated design, which is used for the manufacturing. And how to document this is a good question. A little bit about the future challenges and so short conclusions. So basically we can see that the more development there will be in the automation, different kind of monitoring, and this predictive analysis. AI, big data, data mining, machine learning. Those will try to find your errors or in the simulation try to find you which are the spots that cannot be made. There will be more use of topology optimization, generative design of lattices, voxel-based modeling. There will be more consideration related to sustainability, and basically that's related to design through the optimization, optimized use of materials, energy consumption, and so on. And of course, then we need to educate people, reskill the workforce, and so on. And basically, as usually it's said that in the AM, you need to look the added value. So not only look, example, the manufacturing cost. And then the design is one key to get this added value. Then we need to remember this open source movement. It can be quite good responsiveness, example in this COVID case. Different possibilities in different areas, lightweight, optimized, key performance components, example, you could save fuel, or you make a better medical devices, or in the spare parts where you can get the old data. And there may be one thing if you need to remember is that there will be many 3D models and modifications during the whole process. So how to document those and make a good documentation. So if you need to trace something back, what happened in the different phases. So questions, comments, please.
Thank you, Mika, for your interesting presentation. This is interesting overview of issues that you have to be faced with when you're designing generally parts for additive manufacturing, but especially in medical field, for example, or for a final application of the part, because when you are producing a prototype, it's not so important that you really fulfill all of the functionalities and of the final part, but when you produce it, the final part, then it's quite different and more complex process. Mika, thank you. Thank you for your presentation. So I'm asking attendees if you have any question for Mika. I cannot see any. So Mika, once again, thank you for your support to our project in both workshop and summer school for a really nice presentation. So our next, yeah, thank you. Our next